things into the handouts. So primarily we'll be talking about some basic concept and the use of the concept in the exam. So I understand that you have been expecting spring break and perhaps go out, have a good time a little bit. But then if we look into the schedule, the total number of weeks of the semester is 16. So in fact, at the end of the 5th week, we need to have a midterm exam. So the schedule is already a little bit late. We delay it to week 7 to have the midterm exam. And so this means that this could bother you a little bit for your spring break plan. But I'm hoping that the design of the exam could be more friendly to you. But the way in my mind to do the midterm exam is like divide the exam into 2 parts. Okay. Well, we only have 15 minutes. On April 8th, we only have like the 15 minutes. So in reality, you don't have much time to work on this midterm exam. So basically, we're going to have part 1 and then part 2 for the exam, and this will be until perhaps the say 10 p.m. on the same day. You can, well, for the first part, you do as much as possible on the first 50 minutes. And this will be counted toward 50% of the exam. And because this is only 50 minutes, so it's going to be a closed book exam. You don't have time, you don't have much time to check a lot of things in the textbook or handout. So I'm going to sort of put a lot of concept into this exam. But the same exam paper will be also used for you to continue to work until like 10 p.m. of the same day. And then you detail the answers to get another 50% of the score. And so at the end of this 50 minutes, I'm going to collect your answer sheet, okay? And do as much as possible and do as quickly as possible to earn your 50% of the midterm grade. And then after the class, you use a clean, unused answer sheet to work out the whole set of the exam, and then turn it in through E-class, and to earn the second 50% of the score. And in this process, you can open book, open computer, open everything, try to understand everything in the exam paper. Okay. So this is the design, sort of let you to be more relaxed, I hope. Okay. So this is the design. And usually, for most of the midterm exams in this school, is that you take 2 to 3 hours in the classroom and finish and then it's done. But then I figure that this would be more relaxing for you. All right? Is there any question? For students taking the electromagnetic wave with me, you already went through this, and I hope that you like it. Okay. So when you do the second part, I think you can be more relaxed because you can just check the textbook, check the handout, and have a lot of time to work on it. Okay. Any question about this arrangement? You have gone through this before, right?
So we're gonna have the exam in the morning.
Yes.
It's become 50%, and then we're gonna leave the class, and until 10 at night we have to upload the exams again.
Yes.
But we can also like search the textbook and everything.
Yes. Well, for this part is coursework, and for this part is open book, open everything. And then at the end of this 50 minutes, I'm going to collect your answer sheet. So the teaching assistant is going to distribute the answer sheet and answer paper for you to write on the answers on it. Okay. So at the end of this 50 minutes, I'm going to collect your answer sheet. But then, after this class, then you have many hours to use a new answer sheet, answer paper, to write down the answers, and or just do it on your computer, and then you upload the results to the e-class by 10 p.m. on the same day. Okay, and for this part, you can just read the textbook, read the handout, or look for information from the internet, and try to come up with reasonable answers. Okay. So some people are good at getting score on the ratio, and some people need to work out answers on the ratio. So this is sort of a scheme to accommodate students having different abilities. Okay. Does this sound reasonable? All right. So next Monday we don't have class. You'll be somewhere in Taiwan perhaps for your spring break. And after that, we'll continue the lecture, and we'll have a second meeting exam somewhere, I believe, somewhere on the week of 12. Right. So the schedule of the class is getting tight. So this syllabus is slightly modified, and I put it into the e-class for your reference. Okay. Any more questions? Yes?
Can we change the deadline about the second part? Because I have experiment class on Wednesday, and then we'll continue like until 8 p.m. or something, and I'm afraid that I cannot have time to finish all.
Is it possible to take it on a different day maybe, or before?
Well, we need to finish it in this week.
This exam, the next one, then the next midterm.
You mean this part?
No, the week 12 on 5/11.
You mean you want to change the schedule of the second midterm?
Yeah.
We could discuss that perhaps some other time. Let's first nail down how we're going to do this midterm exam number 1. So somebody has a class, lab class until 8 p.m. on the same day. So
If the deadline changes to 12 p.m., I think I will.
12 p.m. Then you'll suffer until 12 p.m. 12 a.m. in fact. So we can do it 23:59 p.m. Okay. I can move. Well, I can accept it, no problem. So you have a few more hours to work on that. But I suppose that you don't need that much time to do it, but fine with me. Well, quite often that I tell students, an exam is not to defeat you. An exam is to help you to understand the materials. Okay, so it's fine with me that you get more time to work on that.
And the exams are gonna be the exams are gonna be like the quizzes, like similar, just exercises or theory as well?
Anything, the level of difficulty will be higher. Okay, the quiz is just for you to sort of finish everything in 5-10 minutes. So that is very basic. But for the midterm exam, final exam, the level of difficulty in terms of thinking, in terms of the depth of the material will be a little bit more demanding. Yeah. All right, but because we have a closed book exam on the first 15 minutes, I don't think you take much effort to finish everything. Okay. Okay. Well, but final score and also performance will be relative. So just do your best then. Okay. But I tend to make it more friendly for you, so you have a lot of time to think about it and work on it. But then don't push this deadline to the next day, because you could get exhausted if I push this deadline to the next day. All right, so this is the arrangement, and we'll do the midterm exam number 1 next Wednesday, 9 a.m. here. Okay. All right, I want to continue the lecture. Well, we have established the ABCD formalism for analyzing an optical system. And now we want to look into a very important topic in optics, that is the optical resonator. Okay. Optical resonator, being an optical resonator, require a few things. Well, number one, the wave has to be accommodated inside geometrically. That is the very simple observation. And there are other conditions like a phase condition. We're going to talk about it in the later part of this semester. But now let's just intuitively look into an optical resonator, and then think about that. If I want to have a stable cavity or resonator, then we require the light ray to be confined inside this cavity. Okay, so you see that this is a stable light ray propagating through this infinite array of lenses. Okay, an array of infinite set of lenses, and because of this periodical sort of bouncing of the light ray inside the cavity. On the other hand, if you find that the light ray will be at a certain point going out of this lens array, then we say that this cavity is unstable. And this kind of unstable cavity is characterized by some unbounded amplitude of the light ray position and also angle. Okay, so you see that the light ray just go away from this cavity. And so previously we talked about we could model this cavity with an array of periodical lenses. And so if you start, for example, from this mirror, then upon reflection is equivalent to have a lens like this with an effective focal length equal to 1/2 of the radial curvature. Okay. And when the light ray reaches the second mirror, then again this mirror is modeled by a lens with a different focal length. If this radial curvature on this surface is different from the first one. So it turns out that you can construct this periodical array by observing that the periodicity is given by a few ray matrices starting from this lens, ending on the left surface of the same lens. So in this construction, you have two lenses in one unit cell. And then you can repeat this unit cell indefinitely, okay, assuming that the optical light ray is going to be trapped inside. And so this optical system is well defined, and then you can use the ray matrix formalism to construct the ABCD matrix. So let's do the construction. Okay, if we just pick up one unit cell, then starting from a lens, so you start from this ray matrix with a focal length of F1 plane, and then you have the free space propagation by using this ray matrix. And when the light ray meet with this lens, then you use another matrix representing the lens, and then finally you have the backward trip through the free medium. So you have this matrix again. So you have the ABCD matrix. Well, if I go back to this construction, what if R1 equal to R2? The story is going to be slightly different because the unit cell is going to be only half of this. Okay, and this F2 prime is equal to F1 prime. So the unit cell will end here. So that is the simplified. If you have a symmetric optical cavity, if R1 equal to R2, so you cut your unit cell right here. Okay. So when you finish the ABCD matrix calculation, there's only single trip, one way to the second mirror. Okay. But the second mirror is the same as this one. But for this, the unit cell is a round trip propagation. Okay, the light ray starts from here and then complete a round trip propagation. And later, we're going to interpret the light ray based on the number of trips according to the unit cell. So you need to be careful that for this construction, the unit cell tells you a round trip propagation in the cavity. But then if R1 equal to R2, the unit cell tells you the propagation of the light ray from one mirror to the left side of the second mirror. Okay, now let's continue. So bear in mind that we are doing the round trip calculation for the light ray. Right, so once you complete this calculation, you have these results. And then F1 prime, F2 prime are given by these expressions. All right, and because this is the propagation in some homogeneous material, and so the ABCD matrix, the determinant of the ABCD matrix is going to be equal to 1. So this is understood, okay? If you have the, so the propagating the light ray from one material to another material with different refractive indices, then you're going to get the ratio of the index when you calculate this determinant. Well, some people finish this analysis and figure out that well, it will be very convenient if you could define some laser G parameters according to these two expressions. Okay, so this is sort of understood after completing the analysis that if you could define this laser G parameters, then the discussion becomes very easy. Okay, so this laser G parameters is given by 1 minus L. That is the separation, the cavity length divided by 2 times of the focal length. Okay, so in fact this is more like a radial curvature. If you define the laser G parameter to be equal to 1 minus the cavity length divided by the radial curvature of the mirror, then we call this laser G parameters. And if you have 2 cavity mirrors with different radial curvature, then you have G1 and G2 associated with the first and second mirrors. Okay, and this is a very useful definition because we can simplify the discussion a lot after doing this calculation. Well, the reason that this is useful because you are comparing the cavity length with the radial curvature. Okay, because the physics of this, the performance of this cavity is all about is all about the comparing the distance of these two mirrors with respect to the radial curvature. Because the physics is buried inside for this comparison. So with this definition, you can deduce a lot of physics associated with the stability of the cavity. Okay. Well, intuitively, if you have the radial curvature, that is much smaller than the separation of this L, what will happen? It's going to be unstable, right? Because the light is going to go down closer to somewhere here, but the separation of the cavity is very long. So you be expecting that the light ray will just shoot with a large amplitude, with a large angle. So now, in fact, I'm telling you the sort of a little bit the answer in the end of this analysis. Okay, so it's important to compare the length of R with respect to L. With a small R, large L, then it's likely that you have unstable cavity. But if you have an R comparable to L, then it's likely that you will have this kind of stability in the cavity. So Li Xiaorong, can you catch the intuition? Yeah, so it's very intuitive. And quite often that when we see a lot of mathematical expressions, we forget the intuition. That's not right. Okay, always stick to your intuition, and then we'll come up with some reasonable results. All right, once you define it, then this is something that we mentioned on last Wednesday. Mathematician, in fact, can reduce this into a more compact form by taking out this power. Because after n time round-trip propagation, you'll be dealing with this power to the n for this ray matrix M. For this ABCD matrix, the system, the unit cell matrix. And this is going to be difficult. But if you could define some compact form, especially if you define this angle phi, that is equal to this expression. And so we confine this expression to be less than 1, with the magnitude less than 1. Even this goes up to power of n, you still have finite elements in this expression. And then it's likely that the output ray is not going to be, it is not going to diverge. Okay. So under this condition, you can sort of reduce this power of n to a single matrix with power of 1, and the values in this matrix element are still finite. Okay. And this is done by a famous mathematician called Chebyshev. And this is called Chebyshev approach. But some students, in fact, find this more abstract because it's sort of the formula comes out of nowhere. So there are other approaches to understand this. So we'll be talking about the so-called difference equation approach. And this is sort of approach that you can find in almost every engineering mathematics textbook. Okay, it's a very standard approach for solving difference equation. So now you have this ray matrix, ABCD matrix, and after round-trip propagation, you have to raise the power of this matrix to n, so that you can relate the output ray position and output the ray angle to the initial angle and also initial position. Okay, so this is the sort of the basic construction of this system, and so you can just start to write some recursive expression for the nth position and also the nth angle relevant to the previous position of angles. So if you just write two sets of it, the two recursive expression, and we try to put this angle, try to replace this angle with this expression, and then replace this angle with this expression, and you will end up having an expression that is nothing to do with the angle. Okay, just do substitutions. You end up having this kind of results. And the engineering textbook told you that one possible trial solution is to write the solution to be something, some eigenvalue to a power of n after n times of the round trip propagation. Okay, so this is a guessing solution that we can have for this difference equation approach, and this is the standard way for solving difference equations you can find in engineering textbook. Okay, all right. So you put this into this expression you just have, and this expression does not have any angle variables. So it's very easy that you just put it into this, and then you solve for the eigenvalue lambda, and you end up having this result. Okay, you end up having this result. So this is direct substitution. Put this into this expression, but then we use one factor that this f is a determinant of the ABCD matrix, and it's equal to 1 in a homogeneous material. Okay, so we just put 1 into this expression, and then put this trial solution into this expression, and immediately you have this result. And you notice that, well, this is more like a sine. If this is sine, this in fact is cosine, because it's 1 minus something. Okay, and if this is cosine, then you can write down this as sine, because this is 1 minus cosine squared, and you take square root of it. So why not just write this into this expression? Okay, so this is the sort of the Euler's formula, right? You just write this into this expression. All right, so you see that if we are able to write this into this, for lambda to the power of n, this is still finite. So we end up having a very important result that this part, this cosine phi, if I can write this to be cosine phi, then the position after the light ray doing n times round trip propagation, the amplitude of this is still finite. Okay, so we can write into this expression. Okay, so everything is finite, but of course this is something we need to figure out. So important thing is that this is an important step. Once you have this solution, then if you are able to write into this exponential plus minus GFI, this means that we assume this alpha is some sort of cosine of some sort of angle, and this value is less than 1. Its magnitude is less than 1. Then we'll be able to say that well, this magnitude, this is the sort of finite if this is finite. Okay. So we'll start to unfold the physics and requirement for a stability array of the lenses. Okay, so this is sort of a second way to look into this, and so this result is sort of consistent with this result. Okay, if I assume this alpha to be some sort of cosine phi with the magnitude less than 1. Then the elements inside this matrix are going to be finite, and it's likely that we have a stable resonator. So this is the second approach. So to come back to confirm the conclusion from this Chebyshev polynomial. Okay. All right. So the third approach is that if you are good in solving linear system, then we can use a linear system approach to solve the problem. And in double departments, I'm sure that everybody took the class on linear algebra, okay? So in fact, this is the linear algebra problem. Well, if you have an output beam that is equal to a matrix multiplied with the input beam, then because it's the resonator, okay, because it's the resonator, and in the end, we want the amplitude to be finite. Then you can write this the output as eigenvalue multiplied with the input vector, because the library has to come back, and this amplitude is going to define how this system is going to diverge or is going to converge. Okay, so so this is the linear algebra problem. There's an eigenvalue associated with the input after this matrix operation, and this x is equal to the array matrix we typically have. Okay, and this M is the ABCD matrix. So this is an eigenvalue problem basically, and of course we need to look into the condition for this lambda so that we know this is the stable cavity or unstable cavity. Okay, especially after n-time propagation. But then if you go through this eigenvalue calculation, you end up having this eigenvalue. You have, because this is a 2 by 2 matrix. This is 2 by 2 matrix. So you have two eigenvalues associated with it, given by this expression. Okay, and basically you see that this is more like the cosine alpha and this sine cosine phi and sine phi expression on the last page. Okay, and then the linear algebra can also tell you how, based on this eigenvalue, you can calculate the eigenvectors. Okay, you can calculate two sets of eigenvectors. But turn out that these two sets of eigenvectors are linearly dependent. So this means that the basis for this eigensystem just has two vectors orthogonal to each other, and then we don't need to deal with the second set of the solutions if they are linearly dependent. Okay, so this means that all the output vector can be expanded by these two base vectors. So this is what you learn from the linear algebra. Okay, or linear system. So from here on, we'll just throw away this, and then we just look into this set of eigenvectors. And once you have the eigenvectors, and for this linear system, all the output can be expanded by these two bases, the basis vectors. Okay, I hope you don't have much difficulty with this, because this is from your linear algebra. Okay, and if you feel more comfortable to use different equation approach, then feel free to do it. You can also use this approach to get your results. Basically, they are the same. Yes.
On the problem, like, can we choose what to use, or in some problems we choose one approach, on a different problem we choose another approach?
But the final conclusion are the same. Yeah, you choose whatever you look familiar to you. Okay. Yeah, you're going to see that this cosine phi appeared everywhere. Okay, and the laser G parameters, cosine phi equal to alpha equal to this, it show up everywhere in the three approaches. Okay, and some students are good at linear algebra, and then you can just use the linear algebra approach to get the answer. Okay. So the output beam now can be expressed as the any a matrix operating on your input beam, but your input beam can be expressed as the linear superposition of these two eigenvectors. Okay, so I sort of modified the expression a little bit. I put this M outside, and this input beam is the sort of linear superposition of the two eigenvector. And if you put this operator inside, then you get the eigenvector from this operation. Okay. So everybody follow me, right? This x in is expanded by this the two bases of the eigenvectors. And then you put this m onto this eigenvector, you end up having an eigenvalue coming out. So this is the quite straightforward operation. And then if you do a round trip propagation, this is just one round trip, you end up having this. But after n round trip, you end up having this n, the eigenvalue to the power of n, eigenvalue to the power of n. And then from this, you can write down this, because you have this to start with. Okay, this is if you put the eigenvector to this location, you put this eigenvector to this location, then for the position it's going to be this value multiplied with this 1, you get this term, and then this part is going to multiply with this 1 to get this result. Okay, so again, it's a very straightforward variable substitutions. And don't forget that the eigenvalues is given by this, from this calculation, from this calculation. Okay, from this calculation you get your eigenvalues. So this is a standard approach by using linear algebra. All right. So now again, previously we forced this solution round out to be like this. But in fact, it's not always necessary. Okay, when we force this alpha to be equal to cosine phi, we already told ourselves that this alpha has an amplitude less than 1. Okay, but in fact, it's not necessary. Well, the reason that we force this alpha to be less than 1, because we understood that if we force this alpha to be a value, an amplitude less than 1, then everything is finite. The output will be finite and so on. Okay, and then we claim is the stable cavity. But in fact, there are two possibilities. If this is not less than 1, it's possible. If it's not less than 1, if this is not less than 1, it's a possibility. Then we'll say that it could diverge, in fact. Okay, it could diverge. So if we set this alpha equal to some value less than 1, like this, then we can write this expression to be like this. Then this output is going to be finite. Okay, so basically you just have a exponential g phi up to the power of n, but the magnitude is still less than 1. Okay, and we say that this is a stable cavity. So in fact, the claim of this condition is a sufficient condition. It's not a necessary condition, it's a sufficient condition. Okay, if you study logic, and all the students in this country study logic in the high school, right? So you understand what is a sufficient condition, what is necessary condition. Okay, so if we claim the magnitude of this to be less than 1, it's sufficient to say that well, this value will be finite. So it's a sufficient condition. Okay, but on the other hand, if you don't have this alpha, magnitude of this alpha less than 1, in fact, the whole thing could still be less than 1 if you just put some numbers into this. In fact, you can find that, well, it's possible that this alpha larger than 1, but there's a minus sign here. The whole value could still be less than 1. So in fact, even you don't satisfy this condition, the cavity can still stable. Be careful about this. Okay, with certain design of alpha larger than 1, but there's a minus sign here, the cavity can still be stable. Except that nobody wants to bother arguing how to get this alpha larger than 1 and the whole thing is still less than 1. And people just pick up this condition for the design because this is a sufficient condition. when we follow this design guideline, the cavity is already stable. Okay, but be careful that this is the sufficient condition. Okay, I wrote it down here. This is the sufficient condition. Okay, to make sure this alpha is less than 1 when you pick the magnitude. But if you look into this, what really matters is the eigenvalue. Okay, if eigenvalue, the magnitude of this eigenvalue is less than 1, in fact, you can keep this xn to be some finite value. Even you raise the power of this eigenvalue to n, to a big number. Okay, and given this, in fact, what you need to set for the stability is that this lambda is less than 1, but this alpha can be larger than 1 because there's a minus sign here, and the combination of this, even though this alpha can be larger than 1, but this lambda can be smaller than 1. Okay, so this is the sufficient condition, not a necessary and sufficient condition. Okay, it's not a necessary condition; it's just a sufficient condition. Okay, but with this sufficient condition, it's already good for us to design a stable cavity. Okay, so from here on, we'll pick this condition. If we set this alpha to be equal to cosine, this means that the laser parameter G1, G2, the multiplication of these two has to fall between 0 and 1. So this will be the design rule for a stable cavity, but it's a sufficient condition. All right, is there any question? So I stop here a little bit. So if we go back, we sort of went through 3 approaches. And when I talk about Chebyshev polynomial, when I talk about different equation, I did not actually tell you the stability condition. I just mentioned that if we can write alpha into this cosine phi, then everything appears to be finite. That's it. Okay. And when we talk about different equation approach, then we start to realize that there's a power of n on this eigenvalue. So this is sort of reinforced that we should make sure that this factor is less than 1. Otherwise, when n is very big, this can be diverged. So this is sort of reinforced the concept that we should write this lambda into this, and then the output can be finite. Okay, but now we have a rigorous result right here that if we use the eigenvalue approach, then indeed we can prove that when the system satisfies this condition, then the output can be written into a solution on the next page with a finite amplitude. Okay, so this is sort of condition, but this is the sufficient condition, not a necessary condition. All right. Right. Now we want to use one example. Okay. Let's just continue the length array of arbitrary radial curve short for the first mirror and second mirror. Then we now just adopt the necessary condition. So we write this eigenvalue to be exponential plus minus I5 and put it into the calculation. The output is going to be like this from the last page after n time propagation. And because we are able, we sort of force the system to be stable by adopting the sufficient condition. So the eigenvalues is written into this. Okay, and then with this you can write down this xn. Remember that this is the real number, even though we are using complex notation. So we can reorganize this by using Euler's formula into this expression. Okay, and you're going to find that the first term is going to have an amplitude of your input. And this, in fact, can be easily obtained if you recognize that this xe is this expression on the previous page. Okay, this one. This one comes from the x in. Your x in right here is given by this expression, right? And then this is your eigenvector. So your x in is the position is C1 multiplied with 1 plus C2 multiplied with 1. So C1 plus C2 is going to be equal to x in position. So I write here, x in position is equal to C1 plus C2, so you end up having this. Okay. So just follow the same steps. You'll figure out S0. The expression of this S0 is going to be more complicated, relevant to the ABCD elements. Okay, but you can solve for it and do it as a practice. Okay, if you know how to get this expression, then you know how to get this. Just follow the same calculation. Okay. So the conclusion is that for S0, this is also depend on the geometric parameters associated with the cavity. So just do it as an exercise by yourself. Okay. Right. So a few short conclusions. The stability criteria of the resonator, right, is solely depend on the geometric parameters of the cavity. Well, if you look at the definition of stability criterion right here. What is G1 and G2? G1 and G2. G1 and G2 basically is G1 is equal to 1 minus L 2F1 prime. G2 is equal to 1 minus L 2F2 prime. And the G1 and G2 only depend on L and the focal length of the mirror. Nothing to do with the input condition. Okay, that is why we have a short conclusion here. The stability criteria of an oscillator is solely determined by the geometric parameters of the cavity. So this is really nice. If you finish the design of your cavity, the cavity is stable regardless of how we inject the light ray into the system. Okay, so this gives you a very powerful tool to design a stable cavity. Okay, and the second thing is that the ray trajectory depends on both the entrance condition and the cavity configuration. We're talking about this. Okay, if you look at this, the xn, the round trip propagation of the light ray, the position of it depends on the input condition. Okay, and then this is a function of ABCD that is relevant to the cavity configurations. So this is basically the things that we talk about. Okay, so whenever we want to design stable cavity, we just determine the cavity configuration. That is sufficient. Nothing to do with the injection. Okay. And the third part is that don't forget the assumption in the derivation. Okay. It tells you that the paraxial approximation is valid when we talk about ABCD matrix. So you need to confine all the beam very close to the axis. And that is true for most of the applications. But when you deal with a high NA system, then the approximation fail. Then you need to do a more careful calculation, perhaps numerical calculation, by propagating the ray so that you deal with the diffractions. Okay. High NA system means that the ray will come in with the larger angle. And that is the system relevant to, for example, lithography. Okay, people try to use high NA system for lithography to get resolution. And that is something we'll talk about when we touch the concept of diffraction. Okay. Another thing is that in this analysis, we'll assume this mirror is really big. Okay, very, very big. And how big? Well, basically, no matter how big it is, if you find a solution that will diverge, then this means that the system cannot work. Okay, So we just assume that the mean is big enough for this analysis. All right, is there any question after this point? I hope that everything is clear to you. But it's interesting that we use 3 approaches to describe this process, step by step, and then finally we have a conclusion. Okay. So in addition to getting the concept, you also have some ability to do the calculations as well. Okay. And this is sort of the senior undergrad class. So we suppose that you went through the training for engineering mathematics and some calculus. Okay. All right, we're going to have a 10 minutes break and come back.